Not sir. Start ಮಾಡಿ sir.
Good afternoon, everyone. Welcome to day 14, session 1 on solid mechanics by Dr. Umesha P K, sir. To introduce about Dr. Umesha P K, sir, he is currently working as a professor in the Department of Civil Engineering at Vidyardhaka College of Engineering, Mysuru. Dr. Umesha, sir, completed his BE degree in Civil Engineering from the University of Mysore in 1980, securing second rank. M.Tech degree in Structural Engineering from IIT Madras in the year 1982 and PhD degree in the year 2002 from University of Mysore. Dr. Umesha, sir, has worked as project associate in IITM for ISI project on typification of industrial structures during 1980 to 84. Later, he joined Structural Engineering Research Center SCRC Madras as scientist during 1984 in computer aided analysis and design of computational mechanics. He served as head of Tower Testing Research Station of CSIR SCRC Chennai. He is actively involved in research and consultancy for more than 3 decades. He has handled more than 10 crore consultancy projects for government and private companies, both national and international level. He is presently guiding 2 PhD students structural engineering for the dissertation work. He has published and 67 in international and national conferences. He is the editor of 2 books. He has filed 4 patents. His area of research include computational structural mechanics, parallel computing techniques, metal structures, power transmission line towers, telecommunication towers, and finite element analysis, corrosion and fire effects on mechanical structures. He has visited Ruhr University, Bochum under German Academic Exchange Service Fellowship for 2 years to carry research work on parallel computing techniques for structural design optimization. He has visited Research Center Aachen, Germany on technical assignments. With respect to honors and awards received, DAAD Fellowship Award for carrying out advanced R&D in parallel computing techniques for the year 1990-1992 by DAD West Germany. CSIR KFA bilateral program carrying out R&D program in parallel computing techniques, DFG, in the year 1997 June to August. CSIR Technology Prize, that is the certification for appreciation scientific in the scientific contribution in the development of advanced computational methodologies, modeling techniques, and software development by CSIR in the year 1999. And also has received award for parallel computing techniques, excellence in high performance cluster computing 2004 by Sun Microsystems in the year 2004. And also he has received award for the team of CSIR SCRC to receive the Corrosion Awareness Award in the year 2014 for Excellent Laboratory Award in the recognition of meritorious contribution to the field of corrosion science and technology by NASCE International Gateway India section. He is also awarded with Dr. Jay Krishna Prize for Institution of Engineers India for the best paper in Journal Institutions of India Institutions of Engineering Series A during the year 2016. He is also awarded with Sir Arthur Cotton Memorial Prize from Institutions of Engineers India for the best paper in the Journal Institutions of Engineers Series A during 2019. He is a fellow of Institution of Engineers, fellow of Indian Concrete Institute. He is a life member of Indian Association for Computational Mechanics, life member for Computer Society of India, life member of Advanced Computing Society. So this is his a short CV. Now I would like to hand over the session to Dr. Umesha P K, sir. Sir.
Uh, Thank you, Manoj. It's a very nice introduction. Dear participants, today we have day 14 first session on solid mechanics. So today I'm going to cover on solid mechanics topics, that is simple bending theory, flexural and shear stresses, principal stresses and principal planes. So also we're going to cover compound stresses. Compound stresses, if you see here, we'll be having in an actual engineering problem, any problem will be subjected to combination of different stresses. It will be having in a different directions. It will be having a normal stress in all the three directions and shear stresses in the different planes as shown in the figure. So it is a stress at a point you can consider like this. We are interested to have, it can be idealized as like this. So you'll be having the two-dimensional problem. It will be having the stress in X direction, stress in Y direction, and also in the shear stress, that is Q, it will be there in all four sides. That is a normalization, idealization to the two-dimensional problem. So if you see stress in the inclined plane, you are interested to know what is the stress in the inclined plane, that is a normal stress and the shear stress. If it is subjected to uniaxial direct stress, biaxial direct stress, and also general two-dimensional stress. So firstly, let us take, it is subjected to uniaxial direct stress like this. It will be having, so we are interested to know the normal stresses at a plane inclined at theta to the vertical plane. So it will be having the theta here. So P will be the value that is acting in the X direction. So we are interested to know what is the Pn, the normal stress and tangential stress. So that can be resolved in X direction and Y direction and equated to both of them, and we can get Pn is equal to P into cos square theta, whereas P is the actual stress acting on the uniaxial direction. Theta is the angle with respect to vertical. So Pn, that is the normal stress acting on the inclined plane, is equal to P into cos square theta. Similarly, Pt is equal to, can be written as, after solving that one, simplifying and solving, Pt is equal to P by 2 into sine 2 theta. So if you take a case of biaxial direct stress, it will be having you will be having the stresses in both directions, that is P1 and P2. So we are interested to know what is the normal stress in inclined plane and inclined at an angle theta with respect to the vertical. So it will be having a P1, P2, and so if you resolve them in X direction and Y direction, and we can get the Pn. So after resolving both of them and taking the sigma x is equal to 0, that is forces in the normal direction is equal to 0, then we will be getting the Pn. Pn, that is normal stress in inclined plane at an angle theta is equal to Pn is equal to P1 plus P2 by 2 plus P1 minus P2 by 2 into cos square theta, whereas P1 and P2 are the stresses acting in bidirectional stresses, that is P1 in the X direction and P2 is in the Y direction. So theta is the angle with respect to vertical. So Pn is equal to normal stress on the inclined plane, and similarly that Pt is the tangential stress, that is shear stress on the inclined plane is equal to P1 minus P2 by 2 into sine 2 theta. So if we take the resultant of force, that is P square is equal to Pn square plus Pt square. So it can be written as P is equal to square root of Pn square plus Pt square. So that after simplifying that one, you will be getting square root of P1 square cos square theta plus P2 square cos sine square theta. So angle phi, that is the resultant stress angle between the result stress P given plane P is equal to tan phi is equal to Pn by Pt. So that is the value inclined at an angle shear stress. So in the general case, if you take a general stress system, that is, we are interested to know normal stress in inclined plane, and it will be subjected to sigma x, sigma y, and tau or tau xy. So it can be shown like this in the figure. So in the x direction, we have the sigma x, y direction, we have the sigma y, and tau is the shear stress acting on the surfaces. So we can resolve them in the x direction and y direction, and applying the algebraic sum of the perpendicular forces in the x direction and y direction. So we'll be getting the angle. This is the angle with respect to horizontal. We are giving theta is equal to theta with inclined plane with an angle theta with respect to horizontal. So we're interested to know what is the sigma theta and tau theta. Sigma theta is the normal stress acting in the inclined plane, and tau theta is the shear stress acting on the surface of AC. So after solving all the things, we'll be getting sigma theta is equal to sigma x sine square theta plus sigma y cos square theta plus tau into sine 2 theta. This is the expression. I think you should remember in the general case, it is subjected to 2 biaxial and shear stress, and then sigma theta at an inclined plane at an angle theta will be given as sigma theta is equal to, this is the value. Similarly, the tangential stress, that is the shear stress acting on this one, tau theta is equal to, after solving under, we'll be getting tau theta is equal to sigma x minus sigma y by 2 into sine 2 theta plus the tau cos 2 theta. This is the expression. That is, all tensile forces are considered as positive, and shear stress developing in the clockwise direction is treated as a positive. So you can consider that is positive means it is a clockwise direction. If you see in the figure here, so with respect to x direction, it will be having the clockwise direction. So that will be considered as positive. So we'll be getting the sigma theta and the tau theta. So that is the general expression. So once if you know that general expression, we are interested to know what is the maximum normal stress on an inclined plane. So that can be written as, so this is the inclined plane, 2 theta and tan 2 theta is equal to 2 tau divided by sigma y minus sigma x. So this is the expression you are giving a sigma theta is equal to, that is the sigma x plus sigma y by 2 plus sigma y minus sigma x by 2 into cos 2 theta plus tau sin 2 theta. So this is tan 2 theta is the plane, inclined plane where it is acting. So after knowing that one, we wanted to know what is the, this is the tan 2 theta, we got it. Then we are interested to know what is the principal stress and principal planes. So what is the principal plane? Principal plane is the where the shear stress is absent. So we are interested to know that shear stress, you know the shear stress formula, that equated to 0. So we will be getting the plane for tan 2 theta is equal to 2 tau divided by sigma y minus sigma x. So from this one, you can calculate the principal stresses P1 and P2. That is, the shear stress is 0 on the principal planes. So sigma n1 and sigma n2, after simplifying that one, we will be getting in this form. So we'll be having the sigma n, that is a normal stress, that is principal stress, equal to sigma x plus sigma y by 2 plus or minus sigma y minus sigma x whole square. So that is plus 4 tau x by tau square divided by. So after simplifying that one, you will be getting, this is the expression. So sigma n is equal to sigma x plus sigma y by 2 plus or minus half into sigma y minus sigma x whole square plus 4 tau. Sometimes we will be calling as a tau xy or tau square. So that is the major principal axis. You will be having the plus sign, and the minor principal stress will be with minus sign. So this is the expression, so we should remember that one. So once if you know the principal stresses, that is major principal stresses and minor principal stresses, we can calculate the maximum shear stress. That is maximum shear stress in terms of sigma x and sigma y. This is the expression. So if you substitute, that is with respect to principal stresses, we'll be getting the expression like this. So you'll be getting the expression sigma tau x is equal to plus or minus half into square root of sigma x minus sigma y square plus 4 tau square. Or in terms of principal stresses, tau maximum is equal to plus or minus half into sigma n1 minus sigma n2. That is the stresses, actually principal stresses. So we should remember all this formula, whatever given here. So that will be useful for you to solve the problems in the gate. I think if you remember all this formula, it will be very easy to solve the problems. Now I'll take some of the examples in the compound stresses. So if you see here, so we have the compound stresses, that is a biaxial loading case. Let us take. So what the problem is, for the plane stress situation shown in the figure, the maximum shear stress and the plane on which acts are. This is the plane stress situation they given. That is sigma x is equal to 100 MPa, sigma y is equal to 100 MPa. So we want to know what is the maximum shear stress and the plane. So they are given the options like this. So they are given four options A, B, C, D. So first option is equal to minus 50 MPa on a plane 45 degree clockwise with respect to x-axis, or minus 50 MPa on the plane 45 at anti-clockwise direction with respect to x-axis, or 50 MPa at all directions. And also it is 0. So we see the formula. So we know the formula tau theta is equal to sigma x minus sigma y by 2 into sine 2 theta plus sigma xy. So that tau xy, in terms of previous in expression I've seen that tau, sometimes they will be putting as a tau xy into cos 2 theta. This is the expression for the shear stress. So if you substitute these values, so what you will get? So sigma x and sigma y both are equal. So you will be getting 0. There is no shear stress. So this term will be 0. Hence the tau theta is equal to 0 in all directions. So whatever directions is there. So our answer will be D. So 0 in all orientations. That is the things they are given. So we'll take next problem. Problem that is for the state of stresses shown in the figure below, the maximum shear stress is. So now what they are given? They are given the sigma x is equal to 2 MPa, sigma y is equal to 4 MPa, tau xy is equal to 4 MPa. Now we are interested to calculate what is the maximum shear stress. So the expression we know sigma max is equal to, in terms of principal stress, is equal to sigma 1 minus sigma 2 by 2. Xy. This is the expression. So that's equal to square root of sigma x minus sigma y by 2 whole square plus tau xy. So in the expression you might have seen they have taken half outside. So if you take inside, it is the formula. So half is coming inside. So that is equal to under square it is there that way. And if you come inside, it will become 4. 4 will get cancelled. So you'll be getting the expression. So previously I shown half of that one. So half of square root of sigma x minus sigma y whole square plus 4 tau xy square. So this is the expression if you take inside. So if you substitute all these values, that is sigma x, sigma y, sigma x, sigma y and tau xy in the expression, so we will be getting 50 MPa is the maximum shear stress. So okay, so we'll take another problem. So it will be having a plate in equilibrium is subjected to uniform stresses along its edges with the magnitude. So there will be nomenclature, it will be sigma xx will be there, or sometimes sigma x. So it will be in the x direction only, sigma xx equal to 30 MPa, sigma y is equal to 50 MPa as shown in the figure. And the Young's modulus of the material is 2 into 10 to the power of 11 Newton per meter square, and the Poisson's ratio they are given, that is 0.3. If the sigma zz is negligible, negligibly small, assumed to be the 0. And what is the strain? That is the epsilon zz. That is the expression. So they given the, either you can write sigma xx or sigma y. So both will be same. So sigma x is equal to 30 MPa, sigma y is equal to 50 MPa is there. So we know the expression. So they are given the answers like this. So they given first one is equal to minus the strain. Now it is a unitless, strain is a unitless value. So they given 4 options. That is minus 120 into 10 to the power minus 6, minus 60 into 10 to the power minus 6, 0, and another option is 120 into 10 to the power minus 6. So we are interested to calculate that what is the epsilon z, that is a strain in the z direction. So this is the value. Sigma x is equal to 30 MPa, sigma yy is equal to 50 MPa, sigma z is equal to 0. So we know the expression for strain in 3-dimensional case. Like we can written like this: epsilon zz is equal to sigma zz divided by E minus mu into sigma xx by E minus mu into sigma yy by E. So that's equal to, so we already know that is sigma zz is negligibly small and is assumed as 0. The first term it getting 0. So they given the mu value, mu is equal to 0.3, E value they given, that is equal to Newton per meter square is there. So MPa is the Newton per millimeter square. So we need to consider convert all the things either millimeter or meter and substitute this one in the expression. So first term will get 0. So if you simplify that one, minus mu into sigma xx plus sigma yy. So yeah, substitute all the things. And I think I am missing here, E should be there here, divided by E. So if you substitute all the value, so you'll be getting minus 120 into 10 to the power minus 6. That is the option A. So please convert all the units to the 1 unit. That is a Newton per millimeter or Newton meter. So it should be there. So here E is missing. So E should be there for the mu divided by E. So that is answer is equal to minus 120 into 10 to the power minus 6. That's the first option. So coming to next problem, that is we'll take a problem with respect to principal stresses and principal planes. So this is the problem stated in the problem. The statement is the state of 2-dimensional stresses acting on a concrete lamina consists of direct tensile stress, that is sigma x is equal to 1.5 MPa, and shear stress is equal to, that is tau xy is equal to 1.2 MPa, which causes cracking of concrete. Then the tensile strength of the concrete in MPa is, so they are given what are the things they are given? They are given sigma x and tau xy. So you wanted to know what is the tensile stress. So how to calculate that one? They are given the options like this. That is, they are given a first option 1.5, 2.08, 2.17, and 2.29. And we know direct tensile stress will be the principal stress, that is maximum principal stress. So first one, it will be have the expression, that is maximum principal stress equal to sigma x plus sigma y by 2 plus option you have to take. So plus into square root of sigma x minus sigma y by 2 whole square plus tau x by square. So we know here sigma x is equal to 1.5 MPa, sigma y is equal to 0, and tau xy is equal to 1.2 MPa. If you substitute all the things in the expression, we'll be getting the value of sigma max. That should be sigma max, that is principal stress, that is 2.17 MPa. So that is the option given in C. So C is the correct answer. So now it is a 2-dimensional stress. They are given only x direction stress and shear stress, and they want to know what is the tensile stress which causes the cracking. So tensile stress is it will be the maximum principal stress. So that's why you are calculating using the formula this one. we calculate the maximum principal stress. That is 2.17 MPa. So there is no sigma y. So only we have sigma x and tau xy. Okay. So we'll take another example. So it will be like this. So in a two-dimensional stress analysis, the state of state at a point is shown in the figure. If sigma is equal to 120 MPa and tau is equal to 170 MPa, now they ask us to calculate what is sigma x and sigma y. So they given the figure like this. So they are given sigma and tau at an angle. It is angle theta. Angle theta, they are given in terms of a triangle. So instead of giving the value of theta, they are given the values of AB. AB is equal to 4 units. BC is equal to 3 units. AC is equal to 5 units. So the problem is you have to calculate what is the sigma x and sigma y using these values. So we'll see the options. They're given the options like this. They are given 4 options. So we want to pick up the which is the correct one. So there we are interested to calculate sigma x and sigma y. So that will be acting x direction and y direction. Now we'll see how to calculate that one. So we know angle theta, sine theta is equal to, from here, sine theta is equal to opposite divided by hypotenuse. So sine theta is equal to 3 by 5. Cos theta is equal to adjacent by hypotenuse, that is 4 by 5. Tan theta is equal to opposite by adjacent, that is 3 by 4. Thus, from the force equilibrium, so stress they are given. Stress into that area, you take the unit thickness. So sigma x into AB, that is the stress into area. So you will be resolving in x direction first. So you take the sigma into sine theta, cos theta. So into area AC into 1, that is a unit thickness. So sigma cos theta minus the tau will be acting in the reverse direction, that is in the x direction. So either you can take either this term, or if you take a right side, it will be minus sign, that is tau into sine theta. So sigma, if you simplify this one, so we know the sine theta, cos theta, AB, everything, AB value, AC value, and sine theta, cos theta, we know. Substitute that one, and computing that value, sigma x is equal to 67.5 MPa. So from this one, we'll be knowing the option C will be correct. Anyway, we will calculate what is the sigma y value. Sigma y, again, you resolve in the y direction. So sigma y into BC, that is the area in that one, BC into 1 is equal to AC into 1, that is a resolution in the vertical direction, sigma into sine theta, plus that is also acting in the vertical direction, tau into cos theta. So we'll be getting sigma y is equal to 213.3 MPa. So option C is the correct answer. So from this one, so what they are given? They are given the values in the inclined plane, sigma and tau. So they are interested to know what is the actual value in the x direction and y direction. So that can be done using this way. So we'll come to next problem. If the principal stress in the two-dimensional case are, so they are given minus 10 MPa and 20 MPa respectively, then the maximum shear stress at the point is there. They want to calculate as what is the maximum shear stress. They are given the option like this, 4 options. That is 10 MPa, 15 MPa, 20 MPa, and 30 MPa. So we know the formula, that is the maximum shear stress can be written as in terms of the difference of principal stresses divided by 2. So this is sigma 1 will be the major principal stress, and that is sigma 1 is equal to 20, and sigma 2 is equal to the minor principal stress, that is minus 10 MPa. So minus of minus, it will become plus 20 plus 10 is equal by 2 is equal to 15 MPa. So always you should remember that is the higher value will be the major principal stress. then lower value is the minor principal stress. So sigma 1 minus sigma 2 divided by 2. So we'll be getting the value tau max is equal to 15 MPa. So option B is correct in this one. Okay. Now we'll take another example. So an axially loaded bar is subjected to normal stress. They are given only normal stress 173 MPa. The shear stress in the bar is. So we will be confusing that one. Only they are given normal stress. What is the shear stress? So they ask us to select from this one. So now you see the formula how it will be. Maximum shear stress is equal to. So what they given only normal stress. So that means principal stress only in one direction they given. So maximum shear stress will be sigma 1 minus sigma 2 divided by 2, that is equal to 173 minus 0. Since they are given only one normal stress, that will be the major principal stress, and minor principal stress is equal to 0. Now, substituting in the value for tau max, sigma 1 minus sigma 2 by 2 will be getting the value 86.5 MPa. So initially, if you see the problem, you will confuse that one. What is the only normal stress given? How to calculate the shear stress? So we should remember only normal stress is given. So that will be principal stresses acting on the x direction and y direction. So the sigma 1, sigma 2. So you'll be getting this tau maximum. So we'll take another problem. So answer will be B here in this case. So consider the following statement. So we have on principal plane, only normal stress acts. On principal plane, both normal and shear stress acts. On principal plane, only shear stress acts. Fourth one is isotropic state of stress is independent of frame of reference. So now they're given different statement. So they are giving the options like this, which statement is correct or correct. So they're giving the 4 options. So 1 and 4. So they given the first one on principal plane, only normal stress acts. And fourth one is the isotropic state of stress is independent of frame of reference. So second one and 2 and 4 and 2 and 3. So which one is correct? On the principal plane, shear stress is 0. Only normal stress will be there. Okay, only normal stress acts. So no shear stress on the plane. So option, so we can see here the different options. So the second option only you cannot take, that is normal and shear stress acts, both are there. And the third option you see here, only shear stress acts, that is wrong. And first one correct, but it is linked with the 4. There is no other go. This isotropic state of stress, it independent of frame of reference. So option A is correct. So 2 and 3 is not correct. 2 and 4 is not correct. 2 only is not correct. First one, 1 and 4 is correct. So we have to select accordingly. So take another problem. If a small concrete cube is submerged deep in still water in such a way that the pressure exerted on all faces of the cube is P. So they are given it is cube is submerged and it's acting pressure P in all directions. Then the maximum shear stress developed inside the cube is, so there what is the value inside the cube? What is the maximum shear stress? They are given the options A is equal to 0 or P by 2, P or 2P. So now this is the concrete cube. It will be exerted different pressures, that is P in all 3 directions. All directions will be there. And what is the maximum shear stress? So if you utilize to the 2-dimensional one, so it will be having the sigma max equal to sigma, tau max is equal to sigma 1 minus sigma 2 by 2. So in all directions, the stresses, that is principal stresses or whatever stresses will be, that will be equal. That is P minus P divided by 2. So this is the expression. So if you substitute that one, you will be getting the value 0. So option A is correct. So now you can see here, Even then it is having all the three directions equal pressure. So we will be equated to only two-dimensional one. So that is the answer. A is equal to.
Here's a result from the web.
Sorry. So we'll take another problem. So this is the state of 2D stress at a point is given by a matrix. So they're given in the form of a matrix. Sigma x, tau xy, sigma y. Sigma x is equal to 100, tau xy is equal to 30, tau xy is equal to 30, sigma y is equal to 20. So these are in the value in terms of MPa, that is Newton per millimeter square. The maximum shear stress in MPa, they are given the units in MPa, that is same unit as given in the problem. So what is the value? So they are given the options, the four options. So 50, 75, 100, 110. So this is the, we are interested to know what is the maximum shear stress. Now they are given sigma x is equal to 100, sigma y is equal to 20, tau xy is equal to 30. So this is the matrix in the form of matrix form they are given. So that is the maximum shear stress. So either you can calculate the principal stresses one way, or directly you can calculate using this formula. If you take the difference of this one, so the difference of tau max is equal to sigma 1 minus sigma 2 by 2. And the first term will go, and this is the one you will be getting. You directly can substitute sigma x, sigma y, and tau xy. The first term, if you take the difference, that will get cancelled. So either you can calculate the principal stresses, or you can substitute directly for tau max equal to for this portion. That is sigma 1 minus sigma 2 by 2, or square root of sigma x minus sigma y by 2 whole square plus tau xy square. So this is the expression. So substituting that one, you will be getting tau max is equal to 50 MPa. So all the units are same. So we'll be getting 50. That is the answer A. Okay. Now let us take another example. For the state of stress shown in the figure below, the major principal stress is 10 MPa. The value of shear stress is. So every problem is tricky. Now you see here, this is the given state of stress. So sigma x they are given, sigma y they are given, tau xy they are given. So they wanted to know what is the value of shear stress. They are not given the shear stress tau xy. Sigma x, sigma xy, sigma x, sigma y, and major principal stress they are given. So we know the expression. So they have given the options like this. The value of shear stress is equal to 10 MPa, 5 MPa, 2.5 MPa, or 0. So what is the maximum principal stress expression? So we know sigma 1 or sigma 2 is equal to sigma x plus sigma y by 2 plus or minus square root of sigma x minus sigma y by 2 whole square plus tau x square, tau xy, tau square. So if you substitute, they are given the value sigma 1 is equal to 10 MPa. So take a sigma 1 expression, that is positive value if we take here, and substitute all the values and calculate. So we know all the things, sigma x you know, sigma y you know, and only unknown is tau xy. So if you calculate that one, substitute here and calculate that one, you will be getting tau x is equal to 5 MPa. So that is the expression B. Okay, so they are given indirectly. They given the major principal stress. They can give either minor. Also, they can give minor principal also, major or minor. Accordingly, you have to take the expression plus or minus. So from that one, you can calculate remaining one. Okay. So we'll take the next chapter, that is flexural and shear stresses. So we know the different expressions in the flexural and shear stresses. So what is the? It also called bending and shear stresses. So I'll take directly some examples for a given force across symmetrical I section. So remember that a symmetrical I section, the intensity of shear stress is maximum at the, so they're telling at the extreme fibers or centroid of the section, or at the junction of the flange and the web, but on the web, at the junction of flange and web, but on the flange. This is the option they given. So they given symmetrical I section. So if they give unsymmetrical, it will be different question. So they are given symmetrical like this. I section about x-axis and y-axis is symmetrical. So the intensity of shear stress. So what is the shear stress? So it will be given like this. So in the flange portion, it will be reducing like this, and in the web portion, it will be increasing like this. So Q maximum will be maximum at the centroid. So option B is correct. That is the centroid of the section. So that is the correct answer because of symmetrical I section. So answer B is correct. Now, if you take another example on bending and shear stresses, so the maximum bending stress induced in a steel wire of modulus of elasticity 200 kilonewton per millimeter square and diameter 1 millimeter, diameter of the wire is 1 millimeter when wound on a drum of diameter 1 meter is approximately equal to. So they given that drum will be there. So over that one, this steel wire will be wounded. So it will be having that steel wire diameter 1 mm and diameter of the drum, that is 1 meter. So they wanted to know what is the bending stress induced in this one. So different options are 50 Newton per millimeter square, 100 Newton per millimeter square, 200 Newton per millimeter square, and also 400 Newton per millimeter square. So we know the formula from the bending theory, M by I is equal to E by R is equal to F by Y. So moment induced in the section divided by moment of inertia is equal to Young's modulus divided by radius of gyration. That is radius is equal to the stress divided by Y. Y is the distance measured from the centroid, neutral axis. So E they given. So please convert all the things in one unit. So they given here kilonewton millimeter square. So that will be 2 into 10 to the power 5 Newton per millimeter square. So F from this expression M by I is equal to E by R is equal to F by Y. So either you can use different equations. In this situation, they given the drum of diameter 1. That is the radius they given. So diameter they given 1 meter. Radius will be 500 millimeter. E you substituted here, and value of Y. Y is equal to 1 mm. So 0.5 mm you have to take at the edge of that one. That is the maximum stress. So I think this is 10 to the power 5. So 2 into 10 to the power 5 into 5 divided by 500. So we'll be getting 200 Newton millimeter square. Okay, that answer will be C value. So take another example on bending and shear stresses. So here a homogeneous simply supported prismatic beam of width B, depth D, and span L is subjected to a constant load of magnitude P. So they given the section, prismatic section, width and depth, and the span they given, it's subjected to magnitude P. The load can be placed anywhere along the span of the beam. The maximum flexural stress developed in the beam is. So now they're asking, so what is the value of maximum flexural stress developed in the beam? They are simply supported the given prismatic section. So we wanted to know they are given different options like this, A, B, C, D. So we know that one, when the constant load is placed at the midspan. So simply supported, if we place it at the midspan only, we'll be getting the maximum bending moment. So maximum bending moment will occur at the midspan. So we have the formula M by I is equal to E by R is equal to F by Y. Using that one, you can calculate what is the stress. So moment, you know, for a simply supported prismatic beam of span L, that is the maximum moment will be PL by 4, and the bending moment of inertia I is equal to BDQ by 12. Then using the ratio of M by I is equal to F by Y, F is equal to M Y divided by I. So substitute that one you will be getting 3 by 2 PL divided by BD square. So we know that one also stress is equal to M by Z. So BD square by 6, if you substitute, we will be getting the same value. So that is the expression. So D is the correct, 3 by 2 PL by D square. So M by Z, remember either M by Z, pressure is equal to M by Z or My by I. So the maximum stress will be at the outer surface. Okay. Now we will take another example on bending stress. A beam with a cross section given below is subjected to positive bending moment, causing the compression at the top. So if you have compression at the top will be there and tension at the bottom of 16 kilonewton meter acting around the horizontal axis. The tensile force acting on the hatched portion, hatched area of the section, cross section is, so that means they are given the section like this, beam, cross section given below here, it is subjected to a positive bending moment, that is 16 kilonewton meter, and we are interested to know what is the tensile force acting on the hatched area. So now, how to write this one? So what are the options? They are given options, say A, B, C, D, 0, 5.9 kilonewton, 8.9 kilonewton, 17.8 kilonewton. So stress diagram can be written like this. So they are telling it is a positive bending moment of kilonewton around the horizontal axis. So this is the horizontal axis, it will be 0 here. And this is the hatched portion from the neutral axis, below that one they are given. So they want to know what is the tensile force acting this portion. So what you want to know, they are given the maximum bending moment they are given. So that we have the M by I is equal to E by R, F by Y. F is equal to M by Y, My by I. So they given directly moment is equal to 16 kilonewton meter. Y the distance from here to here, that is 25 mm. At the distance Y is equal to 25 mm. I they are given the section C here, the 50 plus 50, that is B is equal to 100, and depth is equal to 75 plus 75, that is 150. So BDQ by 12 is the moment of inertia. So you can calculate the stress is equal to M by My by I. So M also they given. So please convert all of them to the same unit. That is more important. So kilonewton meter. So you have to convert into Newton millimeter. This also in millimeter. This I also in millimeter to the power of 4. So substitute all this one, you will be getting this one. So now we are interested to know what is the tensile force acting on the hatched area. Hatched area means this is the area. So area into the stress value. So area is equal to, that is 25 into 50 is the area. 25 into 50, that is half into, this is the value that given here. So 14.2. So total tensile force will be approximated to 8.9 kilonewton. That is the option C will be the correct value. So what you have done here, Y at a distance Y from the neutral axis, Y is equal to 25. From figure you can see here, Y is equal to 25 you have taken. So you substituted here M is equal to this value in Newton millimeter, and Y is equal to in 25, and I also calculate from here, that will be millimeter to the power 4, and we got the stress in Newton per millimeter square, and calculating the area into stress, we will be getting the total tensile force. Now we'll take another example. I section of a beam is formed by gluing wooden planks as shown in the figure. So this is the figure, that is it is glued like this in all four sides. If the beam transmits a constant vertical shear force of 3000 Newton, the glue any of the 4 points will be subjected to a shear force, that is in kilonewton per meter length of. So they want to know what is the shear force acting at the junction. So they are given the values for the ABCD. That is, they are given already here, kilonewton per meter length. So A is equal to 3, 4 is equal to, B is equal to 4, 8, 10.7. So how to calculate that one? So the shear stress you have to know. So here the portion you are interested to know, you will take one portion ABCD. It is glued at this point. This is the shear flow acting in the I section like this. Okay, this is the dimensions of 50 mm, 200 mm, 50 mm. So bottom also they given 50, 75, 75. So this neutral axis. So we'll see in the next page. So this is the value. And see here, consider the shaded portion. This is the shaded portion you are taken here. That is area ABCD of the plant. The shear flow is equal to Q is equal to shear force Q, that is acting, the shear flow will be acting that one divided by I. The shear flow is measured as a force per unit length along the longitudinal axis of the beam and over the cross section as shown in the figure. Q is equal to A into Y bar. So whatever A is there from here and Y bar from the neutral axis to the centroid of this section. So the area of this one, 75 into 50, that is the area. Y bar is equal to from the neutral axis. So 200 by 200 plus another 25, that is 125. That you will be getting the Q value. Okay, Q value will be getting this value. Then moment of inertia I of the section about neutral axis. So you can calculate moment of inertia of the I section, take the total minus deduct this one. So you can calculate that one, that will be getting 315 to the power of 6 millimeters to the power of 4. Then shear force they are given in the problem previously I have seen in the previous page, that is P is equal to 3000 Newton. So you can calculate Q is equal to 4.08 Newton per millimeter. So the resistance offered by the glue to keep I section intact, Q is equal to 4.08 Newton per millimeter. So you can equal to 4.0 Newton per millimeter. So option B is the correct value. So nearing to 4 value. So 4.0 will be getting. So this is the one. I think we know that one shear flow you calculated and what is the shear for area into y bar, and we know we can calculate the moment of inertia and shear for the given, and Q is equal to that shear flow value VQ divided by I is substituted, and we calculate the value of Q. So for this portion only, so it will be at a distance 125 from the center. Okay. So we'll take another example. The shear force at the neutral axis in the beam of a triangular section with a base of 40 mm and height 20 mm subjected to shear force 3 kilonewton. So what are the value that shear force at the neutral axis they wanted to know. So this is the triangular portion. So they given the base 40 mm, height is equal to 20 mm. So if you take the centroid of that triangle at a 2/3 from the top, so 2/3 of 20 is equal to 40 by 3, and that is 40 by 3 from the top. So what is the width? Width you have to calculate, that is this point. So width at a distance 40 by 3 from the top, so that will be equal to this point. You can take the similar triangle, you can calculate 80 by 3, you will get the millimeter, and shear stress is equal to tau is equal to shear force A y bar by IB. So here the shear force they given 3 kilonewton, that is converted into Newton. Area. So from the this one above this one, from the neutral axis there, what is above that one you have to calculate the area, that is half into base, that you calculate the base width, that is 80 by 3, and the height is equal to 40 by 3, and y bar of this portion, that is 1/3 from the bottom, 1/3 of the bottom, that is 1/3 of 40 by 3 y bar. So moment of inertia of the triangle having its axis passing through the centroid. So passing through its centroid, so parallel to the base. So that will be given as BH cube by 36. So B is 40, H cube is equal to 20, BH cube by 36 millimeter to the power of 4. So B will be width at this point, that is 80 by 3, that is a millimeter. So substitute all these things in the expression here. Tau is equal to SA by y bar divided by IB. So you'll be getting tau is equal to 10 MPa. That is solution C. So so stress will be in Newton per millimeter square. If they are not given, if we see here in the answer, it will be in the Newton per millimeter square. So take another example. So maximum tensile stress at the section XX shown in the figure. This is a figure. So they wanted to know what is the maximum tensile stress at the section XX. So they given the options like this. There are 4 options they given. So we'll take the free body diagram of this one. So at the x-axis will be there. So this is the force acting at this point P. So this is the centroidal distance for this portion. So when it comes to at the x-axis, the section reduced from d to d by 2. Hence, this axial force can be transferred into axial force and a moment. P and a moment. Okay. So that will be acting centroidal of this portion, that is d by 2. So this is a free body diagram of this portion. So now you see how it will be. So the maximum tensile force at the section XX will be, so you know that one, stress is equal to P by A plus M by Z. So now you translated the value, this value, whatever value acting to the centroid of this portion. So P by A plus M by Z. So at the section XX, what is the area? So this is a breadth B they given, and here only d by 2 will be there. So area is equal to BD by 2, and moment will be by 4, that is the moment. So Z, what is Z? BD square by 6. So D is equal to D by 2 here. So that is Z you can calculate and substitute in the above equation, that is P by A. We know P value is there, area you know, and M you know, and Z you know. You substitute all the things, you will be getting the 8P by BD. So that is option A. So what you have done? So maximum tensile stress they wanted to calculate at a section XX. So we have load acting at this one, and it will be taken as this. So equivalent force and a moment. It will be resolved like this. Okay. So from that one, you can calculate the tensile stress P by A plus M by Z. So we'll take another example. A symmetric ice section with a width of flange 50 mm, thickness of flange 10 mm, of steel is subjected to a shear force of 100 kilonewton. Find the magnitude of a shear force, that is in Newton per millimeter square, in the web at the junction with the top flange. So this is the thing they are given. So 50 they are given, 10, and this is section 100, like this sections will be there. This is the neutral axis. So they wanted to know what is the magnitude of shear stress in the web at the junction of this top flange. So we can calculate the I of the I section, that is moment of inertia, that is total moment of inertia minus deduct this one, that is 20 plus 20, 40, 100 cubed by 12. So this is the total section, that is 50 into 120 cubed divided by 12. That's the value. Then they given the shear force S is equal to 100 kilonewton, B is equal to, at that point, at this junction, P is equal to 10 mm, and area of this section 50 into 10, and y bar from the neutral axis, that is 50 plus 5, half of this 10, 5, that is 55. So substitute in the expression Q is equal to SA y bar by IB. You will be getting 71.12. Okay. So we'll take another example. A 450 long plain concrete prism is subjected to a concentrated vertical load as shown in the figure. The cross section of the prism is given as 150 by 150. Consider the linear stress distribution across the cross section. The modulus of rupture, they wanted to know what's the modulus of rupture in terms of MPa. So this is the one. So they given the figure like this, and a simply supported beam with a roller support here and hinge support and 11.25, and the reaction you can calculate, that is both are equal distance from the support. So both the reactions will be equal. So once if you know that one, you can calculate the moment. Moment at C is equal to 11.25 into 150 Newton millimeter equal. and y is equal to section, the given prism section. So 150 is the depth, 150 divided by 2 is the y at the exterior portion, and the section will be 150, that should be BDQ by 12. So 150 to the power of 4 by 12, that is moment of inertia getting. Then stress is equal to m by I into y. So you substitute that one, you'll be getting 3 MPa. So okay. So what the modulus of pressure? So answer is equal to 3 MPa. So one more example, if you take cantilever beam of length 2 meter with a square section of side length 1.1 meter is loaded vertically at a free end. The vertical displacement at the free end is 5 mm. The beam is made up of steel with the Young's modulus of 2 into 10 to the power of 11 Newton per meter square. The maximum bending stress at the fixed end of the cantilever is, so they are given the sections like this. It's a 2 meter and section they are given 0.1 by 0.1 is a P is acting. They want to know what is the bending stress at the fixed end of the cantilever. So this is the options they are given, the 4 options. So we know that you can calculate the I value, and we know delta end, that is a PLQ by 3I. So that's equal to, they given you convert into the meter. So E they given, length we know, and P can be calculated from this one, from this expression 1. So that you will be getting 3125. So substitute the value here, P only, all value you know. And from this expression, M by I is equal to E by R is equal to sigma by Fy. So moment is equal to, so if what is the moment acting here? P into L, that is a 2 meter. So P you calculated. So we know the moment, and the depth from the neutral axis is equal to 0.1 by 2. So sigma max is equal to My by I. So you'll be getting 37.25 from this one. The answer B is the correct answer. So now we will take up the problems in slope and deflection of beams. So we should know all these expressions for the different beams subjected to constant load, UDL, uniformly distributed load, and moment. This is a cantilever case. You can see here the slope they given, and deflection at any section in terms of x. They given the value, and the maximum deflection at the tip. They given the maximum deflection. So you should remember all this formula, or you should know how to remember. Okay, this is for the cantilever one. And similarly for the simply supported, we'll be giving the expression for the slope, deflection in terms of x at any section, and the maximum center deflection. So we'll be knowing the values of this one, deflection, slope you know, deflection you know. So for the different loading conditions, that is constant load at the center and the load at the different point, UDL, and a moment, and a uniformly distributed load. So these are the expressions. I think one should remember or know how to calculate that one using the M by EI diagram. So we'll take up some problem. So a cantilever beam of a span L is subjected to a downward load of 800 kilonewton uniformly distributed over its length, and concentrated upward load P at its free end. For vertical displacement to be 0 at the free end, the value of P. So what they given here, they given the total value of the UDL. That is UDL 800 kilonewton for a length of L. It's a cantilever one, uniform distributed, and they want to know the P is acting here. Vertical deflection displacement will be 0 at the free end. So what is the value of P? So now we know the UDL acting in the from top, and it will be supporting so that there is no deflection. So what is the value of P so that we can arrest that deflection? So this is the expression. They are given the different options, and you can see here for the vertical displacement to be 0 at the free end, the vertical displacement due to UDL should be equal to the upward displacement due to P. So that means deflection due to UDL equal to deflection due to concentric load acting from the upward. So both are equal. So if you equate to that one, so UDL is given directly WL they are given, the total load they are given, that is W is equal to 800 kilonewton. And in this expression, I think previous slides have shown this value WL to the power of 4 divided by 80i is equal to PLQ by 3i. So from this expression, you can calculate the P is equal to 3 by L, WL. So you get P is equal to 300 kilonewton. So if you put a 300 kilonewton, it can arrest the deflection. There is no deflection for at the cantilever point. Okay, we'll take another problem. A cantilever beam of a span is supported uniformly distributed W per unit length, resting on a rigid right prop at the tip of the cantilever. The magnitude of the reaction at the prop is, so again here they given in terms of unit per length. So similar way you can calculate. So they given directly the values. So the reaction will be, so reaction R will be the tip of the prop support. So deflection at the prop support equal to 0. So this is the expression WL to the power of 4 divided by 8 EI minus R is the reaction, that is equivalent to R LQ by 3I. So we can calculate R is equal to in terms of WL. That is a 3 by 8 by WL. So that is option C is correct. And go to next problem. Deflection of a cantilever beam at the free end be applied with a moment at the same point. So what they are giving, this is a cantilever beam. It is subjected to a moment. So you want to know what is the deflection of the cantilever beam. So what are the different options they are given? I think if you remember the formula, we can give directly. Otherwise, we can calculate that one. So this is the moment acting at this point. So moment for the cantilever beam is equal to M by EI diagram like this. So what is the deflection at the cantilever is equal to, so area of the M by EI diagram into center distance at that point. So A into X bar. M by EI into L. This is the length. So area of that one, ML by EI into L by 2 at a centroidal distance. So ML square by 2 EI. So option B is correct. So if you know directly, you can substitute that one. If you don't remember that one, you can go by M by EI diagram and you can calculate the value of deflection. That is the area into X bar from the end with respect to A. Okay, then we'll take another example. A cantilever beam of span L is loaded with a concentric load of P at the free end. The deflection of the beam at the free end is, so this is also easy. I think if you remember that one, you can directly you can put the value directly. Otherwise, if you don't remember, go to M by EI diagram. So what is the M value at the point is equal to P into L, PL by EI. So value, you can calculate the downward deflection of a beam AB at the free end. That is B is area of M by EI into centroidal distance. So area is equal to half into base into height into 2/3 of the length from here. So that is a PLQ by 3I. Option 3 is C is correct. Okay. So we'll take another example. Sorry, I think points are coming here. A cantilever beam is shown in the figure. The moment to be applied at the free end for zero deflection at the point is. So now they want to know what is the moment to be applied at the free end for zero vertical deflection. Previously we calculated what is the vertical support. Now for the UDL, now they given the vertical force and applied the equivalent moment in the reverse direction so that it can arrest the deflection. So they given the different options here. So the problem can be written like this. So they given the problem like this. They given the cantilever with a vertical load. That is, you can write as a M by EI diagram. And this is the moment. In the opposite direction, we will be having the moment. That is in the clockwise direction. It is the anti-clockwise direction. So both will be equal, and the deflection deflection at the this pre-end, that is A end, will be 0. So what is the deflection for this one? So add both the things, you will get 0. So that means a downward deflection of beam AB at the free end. B is the area of M by EI and the centered distance. So first, this is a negative one. So A into X bar, if we take half into base into height, that is 4 by 3. And here M by EI into the length into the centered distance. So we know we can calculate from this one, M is equal to in the clockwise direction. So they're confusing. So they're given both the clockwise and anti-clockwise. So it should be in the clockwise direction, reverse to this one. So moment will be applied at that point in the clockwise direction. So option C is correct. We'll take another problem with the deflection. A stepped cantilever beam is subjected to a moment M, as shown in the figure. The vertical deflection at the free end, neglecting the self weight. So this is the moment they're given for different sections. So first portion will be having 2 EI, that moment M is acting here. EI is there, again moment is acting here for a length L by 2, L by 2. Now the option will be given for the vertical deflection. Here given here. So we can calculate the bending moment. This is a bending moment diagram. So from here to here for L by 2, that only moment M is there. So M will be here and it will be add up another M. So M plus M, it will become 2M. So what is the M by EI diagram? So if you see the M by EI diagram, this is only one EI is there here. M by EI portion, if you take here, that will be M by EI. And here 2M divided by 2 EI. So again, it will become M by EI only. So M by EI diagram, it will be simple or it will be rectangle one. So take the deflection with respect to A. So moment of the area of M by EI diagram between A and B about B and the centroidal distance. So if we calculate that one, we will be knowing deflection at M L square by 2 EI. So that is option C is correct, M L square by 2 EI. So we'll take another problem. A cantilever problem PQR shown in the figure below. A segment PQ has a flexure rigidity EI and segment QR is infinitely flexural rigidity. So this is very rigid one and this is having the flexure rigidity EI. So what is the problem? So they're given the options like this. First problem, they will be connected to two problems. They'll be having the, what is the problem is the deflection and slope of the beam at Q. They want to know what is the deflection and the slope at Q, this point. So they're given the different options here. So they want to know at Q only. This is a rigid portion and the value, the load is acting at the free end. So free end load can be transferred into a equivalent vertical load and a moment. So equivalent vertical load W is acting at a distance L and a moment is equal to W into L. So you can calculate for this portion, that is the first portion, that is flexure rigidity EI, the cantilever beam, it will become a cantilever beam and can be modified as shown in the above. The deflection at Q is equal to, that is deflection due to vertical load, deflection due to moment. Both if we add, we will get the deflection here. And similarly, you can calculate the slope. So you should remember all the formula for the constant load, moment, and UDL and uniform distributed for cantilever and supported beam. And in this case, only cantilever one. So you'll be getting 5 deflection at Q is equal to 5 WLQ by 6 EI and slope at Q is equal to 3 WL square by 2 EI. They are combined both the things and asking. Answer will be at A. See here, this is the value. So this is a rigid portion. The first portion, they given the two problems for the same, this one, and we'll go to next page and the same problem will be there. So now what they're asking, so they want to know what is the deflection of a beam at R. So they want to know what is the deflection at R for the same beam. Now, how to calculate that one? So we have the rigid beam here and deflection for the first portion, that is flexure rigidity EI. We have the delta 1 and this is a rigid one. This is a straight, it will deflect as a straight one, that will not any curve one. So that will be delta 2. So we want to calculate delta 1 due to this load, and delta 2 due to that vertical one, that slope into the distance you can calculate. So since the QR portion is the rigid one, QR remain straight. Deflection at R is equal to delta 1 plus delta 2. That is the deflection at Q plus slope at Q into R. Because it's a straight one, you can take as a small value, that is the slope into the length of the beam. So we can calculate delta is equal to 7 WL cube by 3I using this formula. So we'll take another, the answer will be C, answer is correct. We'll take another last example. So for the cantilever beam of a span 3 meter shown below, a constant load of 20 kilonewton applied at the free end causes a vertical displacement of 2 mm at the section located at a distance 1 meter from the fixed end. If the concentrated vertically downward load of 10 kilonewton is applied at the section located at a distance 1 meter from the fixed end, the maximum vertical displacement of the same beam is. So now what they're telling, they applied a 20 kilonewton at this point, you get the 2 millimeter deflection here, and you apply the 10 kilonewton here, and what is the deflection? Delta 2. So what is the logic here? So I think you know that one, Betti's law. From the Betti's law, the maximum deflection at B can be calculated from the Betti's law. That is the P1 delta 1 is equal to P2 delta 2. So we're interested to know delta 2. 10 into 2 is equal to 20 into delta 2. So delta 2 is equal to 1 mm. Okay, that is answer you have to put 1 mm. So by this I will stop here. If you have any queries, you can send to me any email, or you can contact over email or my mobile. All the best. Good luck for your exam. Thank you, one and all. Go to our MC, Manoj. Thank you, one and all. Bye.
Thank you, Umesha. So I request all the participants to join us again at second session today at 3:45 p.m. using the same YouTube channel. Thank you. Thank you all.